Hi guys, this is the first video in our coverage of erasing a pair from a binary search tree. We're going to start with one part of that process, which is removing one particular node from the tree. So the whole process of erasing a key value entry from a binary search tree involves a bunch of steps, but one of those steps is once you have a particular node targeted to be removed, you got to get that node out of there and update all the pointers surrounding that node correctly. So we're going to start there. It's maybe the most subtle part of this. Once we kind of get past this obstacle, the rest of the approach will be a little more straightforward. So yeah, this video is focusing just on this one part of removing a particular node from a binary search tree. We're going to develop a operation RemoveNode U. So U is a pointer to a particular node that needs to be removed. What RemoveNode does is remove that node U from the tree and update any incoming pointers to that node, the incoming parent or child pointers that point at U. So that's all it does. So this assumes that U is a pointer to a node. It's a valid pointer that was found through some other process. We'll get into how that happens later. Also, RemoveNode updates the tree's root if necessary. So this is kind of a high-level approach here. We'll see code for this later. This is a high-level explanation that's suitable for running by hand or in my slides here. Later what we'll see is the entire erase key pseudocode, the entire process of erasing a given key from the tree, and also C++ code for this and all the other functions in order to do that operation. So here's kind of the challenge. When you remove a node U from the tree, it kind of leaves a quote-unquote hole. There's a gap where a node used to be. And we need to maintain this binary search tree structure where parents are connected to children and there's no holes or gaps in there so that the whole tree stays connected. What we want is that after we remove one particular node, the rest of the tree still works. So if I search starting at the top, it needs to still be possible to get down to the lower keys in lower nodes in the tree. We don't want to break the tree that way. So this RemoveNode U operation needs to patch that hole. It needs to find a way to put a node in the gap left by removing that node. And it turns out that there are three cases. It depends on how many children U has. U is the node we're removing. So if U has 0 children, meaning U is a leaf, then we just replace that hole where a node used to be with null, and that's it. It's a relatively easy case. If U has only one child, then we replace the hole where U used to be with that one only child of U. So this is also pretty easy. The one that's complicated is when U has 2 children, then we kind of have this dilemma. Is it the left child or the right child that takes the place of the parent that was removed? We'll get into that in a moment. That one's complicated. First, let's look at the first two simpler cases so we can kind of finish with those. So first, let's see what happens if we remove a node with 0 children. In other words, if we remove a leaf out of the tree. Let's say I call RemoveNode U on 55. So U is a pointer to this 55 node, and the goal is to get the 55 node out of the tree and update any incoming pointers to 55. So that would be any child pointers or parent pointers or root pointers that point at 55. In this case, it's a leaf, so there's only one of those pointers. It's 61's left child pointer. It needs to be updated to not point at 55 anymore. So this is the case of a 0 child node. It's a leaf. That right there is the hole. See, if we take 55 out, now there's this gap. There's this left pointer kind of dangling that used to point at a node, but that's not a valid node anymore. We need to fix this so that the tree is valid. But there's nothing below 55, so we can just safely put null there, and we plugged the hole. So 61's left pointer points at null, and we've got a clean, well-defined binary search tree again. Okay, let's look at the second case. What if I remove a node U that has exactly one child, not 2 children, not 0 children, but one child? So let's say, for example, I remove the root 37. So remove node U. U is a pointer to the 37 node. This here says we'll replace that hole with the only child. So taking 37 out of the tree kind of creates this temporary hole here. There used to be a root node. There's not a root node anymore. But what we'll do is take the one and only child of the old node. It's the 61 node. 61 will take the place of this parent we just removed. So 61 shifts up there. Now 61 is the root. We need to update the root pointer of the tree to point at 61 now. And that's it, we're done. We've got a valid binary search tree again. That's all we need to do. So what happens if the node we want to remove has two children? This creates an obstacle. In this example, let's say I'm removing 61. So U is a pointer to this 61 node. What do we do? Well, if we take that node out, there's a hole here. Something needs to take the place of 61. If I just stop now, 37 points at a invalid pointer that's been freed, and there's no way to start at the root and get down to 55, and no way to start at the root and get down to 83. So we broke it. So we need to solve that. We need to put a node in that hole. But there's a dilemma. There's two obvious choices, 55 and 83, but if we just shift either one of them up, it cuts off the other. And we don't want to do that, right? So let's say I replace this hole with the left child. So let's just take the left child, which is the 55 node, have it take the place of this hole. So 37's right child pointer points at 55. It would look like this. But now this 83 node is cut off. There's no way to start at the root and follow left and right child pointers and wind up at the 83. We broke the tree. 83 kind of got cut out of the tree, even though it's still supposed to be there. And the same thing happens if we pick the right child and promote the right child up to take the place of the old parent. Same thing happens if we just move 83 up there, say 37's right pointer is the right child of U, which holds the 83 in this example. Well, 83's left and right child pointers are null, so there's no way of getting to 55, and now 55 is cut off from the tree, and there's no way to search the tree and end up at 55. So those two approaches are not going to work. We have to do something different. And the solution is to not just look at the immediate left and right children necessarily, but instead to replace the value in node U with the in-order successor of U. This references back to the binary search tree traversals, pre-order, in-order, post-order. We're using the in-order traversal idea here. So let's say we remove a node with two children. For example, here's a bigger tree, and let's say we want to remove the root. Seems like a pretty invasive, disruptive kind of thing to do. So if I remove node U, if we have the same dilemma. If we just promoted the left subtree to come up here, then this whole right subtree is cut off out of the tree. That doesn't work. Same thing symmetrically. If we just move the right subtree up to take the place of the U root, then the whole left subtree is cut out. Neither of those are going to work. But what we could do is go somewhere else in the tree and put a key in this node. If we do that, we have to pick a key that will not break the binary search tree order invariant. So it needs to be a key that is very close to this key at the root. So let's think about what that would be. Remember that we have the binary search tree order invariant. Everything on the left side of the root needs to be a key less than the root's key. Everything on the right side of the root needs to be a key greater than the root's key. So what needs to go here is the next value that's the next highest or the next smallest value in the overall set of all keys. How could we find that? Well, we could find it with our in-order traversal. Remember, the in-order traversal is the one that happens when you follow the Euler tour and you visit nodes when you are underneath them. So here I'm visiting the predecessor of U, and then the next thing that the in-order traversal visits is U itself. Let's pay careful attention to the next key that gets visited in this traversal. The next key that gets visited in the in-order traversal is this one right here that's pointed at with this successor arrow. So that means that in increasing sorted order, if we go through the increasing sorted order, we get to U's key. The very next key that we'll see is this one down here. That's called the successor of U. And because of that, we can take the key in this particular node, copy it up into the root node, and that will preserve the binary search tree order. We then have a little bit of an issue that there's two copies of that key, but that's relatively easy to fix because this is a leaf for sure, and that means it has 0 children, and we saw that deleting a node with 0 children is relatively easy. How do we find the successor? Well, you go right once and then left as far as you can. Why does that work? Because we want the next node in the in-order traversal. So that would mean we can look at the right subtree of the U. That would be the set of all keys that are greater than U's key. That's how right works. And then if we go left, that would get us the smallest element in that subtree. So again, everything to the right of U has keys that are greater than U's key, but we want the smallest of those. It's the next biggest element in the sequence. So going right says give us stuff bigger than use key, and then go left as far as you can. This node on the left side of the right half of the tree is the successor. That's the smallest key that's still bigger than use key. Here's pseudocode for that. It's actually pretty easy. Pointer would point to use right, so that goes down right once. And then as long as pointer left is not null, so as long as this node still has a left child, we do pointer equal pointer left, that moves to that left child. So that will zoom us straight down there and then return that pointer. So here's a little helper function called successor. Given node u, it finds the successor of u, meaning the next node in order traversal is just go right once and then left as far as you can. So for example, let's put some concrete numbers in here. I'm not going to fill in all the keys, just the two that are involved. So let's say the root has 9 key and the successor has 11. That's a valid key here because remember this would have to be a key greater than 9 because it's in the right subtree of 9, but it would probably be pretty close because it's the minimum key that's still bigger than 9. So the algorithm over here was, if u has 0 children, meaning use a leaf, you just replace the hole that's left with null. 1 child, you replace the hole with that only child that you had. And in the case of you having 2 children, this is the new innovation on this slide, we replace the hole with the in-order successor. So what we're going to do is find the successor of 9, you go right and then left as far as you can, that's the value 11. We are going to erase the 9, we're just going to overwrite it and copy 11 up there. So now 11 is the new root, and that is going to be a legal key. It does not disrupt any of the other nodes. We don't need to mess around with any of those. They're still in the right binary search tree order because of this predecessor successor thing. But now there's 2 copies of 11 for a moment, so we need to remove the second copy down in a leaf. But this is the first case. It's definitely a leaf because remember we went right and then down as far as we can, or it definitely has 0 or 1 children because we went right and then left as far as we can. So since we went right and left as far as we can, we know that this successor has 0 or 1 children because it doesn't have a left child. And so it's going to be one of these 2 cases. And so we can just remove this node and know that it will be either the 0 case or the 1 case. We don't need to do this successor thing again because this node will not have the same problem. So that node goes out, and now we're done. We've got a legal binary search tree again. So let's just kind of summarize the whole process here. This is just for removing one particular node out of the tree. You have to look at how many children that node has. If the node has no children at all, meaning that node is a leaf, you just replace that node with null. If u has only 1 child, then you replace node u with that only child. So the one and only child of u is promoted up to take the place of u. Finally, there's the more complicated case. If u has 2 children, then you replace the u node hole with the in-order successor node. So you go to the right and then left as far as you can relative to u, copy that value up into u, and then repeat this process to remove that successor node, and we know for sure that that successor node will either have 0 or 1 children. That successor definitely does not have a left child, so it has 0 or 1 children, and so that'll be a repeat of these easy cases.